Hello and welcome to the 10th part of the series of videos aimed at developing retro games in vanilla JavaScript using the canvas element. My name is Anthony, and please join me in my corner of the web where I like to build stuff in the browser using the latest technologies. By the end of the last video, we'd actually covered most of the basic functionality and movement for a Street Fighter game, to the point where it's looking quite authentic. We've now finished the background of the status bar HUD that sits at the top of the screen. The stage now has its 3D effect floor, parallel scrolling, and various animated objects in the background to give it some life. We're also displaying all the initial fighter and background details in the status bar too, which we'll likely come back to in the next video. So far so good then. But as mentioned, this might be great from a visual point of view, but we're missing Street Fighter's main component, its fighter mechanics. Hopefully then I come bearing some good news. If you haven't seen the video title, we'll finally look to start resolving some of that today. As we bring up our dreaded to-do list and scroll through the available items, you'll see that I've highlighted a number of topics here that we'll look to address in this part of the series. We have a lot to cover today, so we'll start by adding all the basic attacks we can perform from a standard position as a starting point. We'll expand on this in the next video, but this gives us a good opportunity to gradually bring in the attacks so we can understand the fundamentals first. Although to accommodate the attacking moves, we'll first need to update our control scheme to allow for punches and kicks, so we'll do that today also. And lastly, we'll bring in another couple of collision boxes and understand how they work, and how they allow us to detect if the attacking moves have collided with the opponent. So yeah, be prepared, this is going to be a very technical and code heavy video today. And just before we get on with the video, I would like to kindly ask people to click the like button, especially if you find these videos helpful in any way. I noticed that over 70% of people who watch my videos are unsubscribed too, so why not go ahead and do that if possible. Both are absolutely free and will only help to grow this channel, and ultimately give me more emphasis to focus and improve on its content. For those of you who have already done so, either on this video or any of the others, a big thank you goes out to you, as it's extremely appreciated. Okay, let's jump right in. So jumping back into the code for the first time today, we'll start by updating the fighter state enum object, so the game and primarily the state machine is aware that these new attacking moves are available. Underneath the crouch turn property, we'll add each of the 6 new keys, 3 for the punches and 3 for the kicks, to mirror what we've just mentioned. Notice how both sets use the light, medium and heavy prefix, so that we can differentiate the strength of the attack. With those in place, we can now turn to the Ken and Ryo classes and add the necessary frame details and animations for these moves, just as we've done previously. Again, I'll be pasting in the code and data that I prepared earlier. If you wish, you can pause the video here and copy what you need. Just to make things a little clearer, we'll start by just handling the light punch move and frames for now, before we move on to the other attacks. Once these have been defined, we'll jump back to the fighter class and continue to add its behaviour to its state machine. To do that, we'll add its new key, light punch, along with setting up the new function names for the init and update properties. As we know the light punch is a standing attack, we'll add the idle and walking states into the valid from array, just to ensure we don't transition from any invalid states. Let's then add our new init function, handle standard light attack init. And inside we'll just be calling the handle idle init function for now, which we know from past videos will simply reset the fighter's velocities. As for the update function, handle light punch state, for the time being we'll just check to see if the animation has completed, and if it has, we'll revert back to the idle state. As we are reverting back to the idle state, let's ensure we add this new state to the valid from list for the idle state in the state machine too. Next, as we know the light punch attack is instantiated by the idle state, we should look to add a button or key press check in the handle idle state function to enable this. Although we have now hit our first blocker, we don't have any controls currently set up to handle the attacking moves, so we'll need to tackle that problem first before we can continue. In the control.js module then, in the control object, notice that we currently only have the directional buttons configured. We'll start by adding the attacking moves here, so that the game is aware that these new buttons exist for each control device. Basically though, we'll just be copying over the new fighter state keys we created earlier over to this object. Next we can move on to updating the controls array and configure the control devices themselves, adding the designated button and keys for each action, although for now we'll continue the trend and only focus on the light punch. So in each of the gamepad and keyboard property objects, we'll assign a new button ID and a key reference to the new light punch control. If you'd like more information on how the controls work in general, I'd highly recommend looking at part 6 of the video series if you haven't already, as I won't be going over it too much here. If I've remembered, there should be a link in the top right hand corner somewhere, although as a general quick recap, these new lookup values will be mapped to event functions within the input handler module to determine if the button or key has been pressed. For myself, I'll be using button index 0, which corresponds to the A button, as I'm using a 360 controller, and copy that value to both gamepad objects. As for the keyboard, I'm using the control left key for player 1, and the Q key for player 2. As per usual, you can use whichever buttons and keys you prefer here. Okay, with the controls now configured for use, we can look to update the input handler code. We'll start by creating a new control helper function called isControlDown. This function is similar to the other isDown helper functions we have above, but this one will be used to determine if a particular control is held down instead. It will take a player ID and a control type from our enum object as parameters, which in turn will pass on to the isKeyDown and isButtonDown functions using the controls objects we just configured. So in summary, if either of these functions return true, then we know either the keyboard or the gamepad currently has this control held down. Let's jump back to our fighter class and put this into action. We'll replace the current dummy code with the new isControlDown call instead, and pass on the player ID property from this class, and the light punch type from our main control enum object. If this is true, we'll then finally change our current fighter state to our new light punch attack state, and with that, we should have enough to see some results in the browser. Great stuff! Both Ryu and Ken are now able to perform their light punch using the controls we have configured, although we have hit our first issue. If we were to keep holding down the control, they will continue to perform the punch, which is not the behaviour we're looking for. Having access to the held buttons was absolutely what we needed for moving the fighters around the screen, but for the attacking moves, we need to tackle this a little differently. Referencing the original game, for attacks it would only register the button once, regardless of how long it was pressed down, meaning the button would first need to be released before it would respond again. To allow us to accommodate this behaviour in our game, we'll need to go back to the input handler module and make some changes to handle this. We'll start by adding two set object constructors, one for the keyboard and one for the gamepad. I'll be calling these press keys and press buttons respectively. Just like the held counterparts we have for these controls, these objects will hold unique references for just the currently pressed keys or buttons. Starting with the keyboard, let's create a new function called isKeyPressed, alongside the other isKeyHelper functions. Just like those, it'll take a key code as its parameter. Now inside this function, we'll check to see if this particular key is held down, and if it is, but we don't have a reference in the new pressed keys object, we'll simply add it and return true. However, if the key reference does not exist in the press keys object, we'll return false, as we know we've already performed this event once before. Now that we're recording the key references into the press keys object, we should look to remove them when the keys have been released, so that we can trigger another key pressed event. Thankfully, this is easy as adding a delete call inside the handle key up function, which we know is called exactly when this event happens. Straightforward enough. Moving on to the gamepad, we'll again add a new function and call it isButtonPressed. Similar to the button helpers above, we'll again add a pad ID and a button ID as parameters. The difference here, however, as we're working with multiple gamepads, we'll need to create a unique key for the pressed button set object. To do this, we'll use the parameters and interpolate them into a string, which should be unique enough for our needs. The rest of the function follows the exact same logic as the isKeyPressed function we've just created, obviously using the isButtonDown function and the pressButtons object. But just to clarify, this will use the key we defined and check to see if this exists in the pressButtons object. If it doesn't, we'll add it and return true, but if it does, it will return false. As for removing the keys from the pressButtons object when the button is released, we unfortunately don't have any released events to hook into for the gamepad, so we'll have to be a little creative and come up with something ourselves here. In the pull gamepads function, we'll loop over the buttons while checking to see if they exist in the pressButtons object, using the same generated key reference. For this, we'll use the gamepad index and the button index and again interpolate them into a string. We'll also check to see if the button is no longer currently pressed down, using the isButtonUp helper function we previously created. If both of these are true, we can safely remove the button reference from the pressButtons object. And with that, we should have enough to cover both the keyboard and gamepad press events we'll need for all the attacking moves. Although, to follow the trend, we'll create one more helper function called isControlPressed, next to the isControlDown function. This new function will work in exactly the same way too, but this time we'll use our newly created isPressed functions instead. Let's now go change the fighter class and use this new helper function and see how it affects the results in the browser. Looking good! When either the light punch button or key is held down, Ryu and Ken will only trigger the punch animation once. If we want to perform multiple punches, we'll now need to keep tapping the button, which is exactly the behaviour we wanted. Although to make this a little easier on ourselves moving forward, let's add one more helper function to the input handler module. Following the other control functions we set up in part 6 of the series, we'll now add a new function called isLightPunch, which will simply alias the isControlPress function we just created. The advantage here is that this will remove the extra complexity of passing in the light punch control constant into the fighter class. So let's go ahead and do just that at the bottom of the input handle module. Once complete, we'll jump back to the fighter class and fix up the code within the handle idle state function for the last time. And there we have it. We have Ryu and Ken's standing punch attack move now working in its basic form. Although, light punches have a special case that we're not catering for at the moment. As mentioned earlier, light punches are sometimes called jabs for a natural reason. But before we go into what that means, let's first take a little detour and explain how basic attacks work. Most attacks can generally be broken down to 3 phases. There's arguably a 4th, but we'll come on to that later. These 3 phases include a startup phase, which is the time or the amount of frames until the attack can cause damage, an active phase, which is when the attack can cause damage, and a recovery phase, which is the time or the amount of frames until the attack completes and the fighter becomes responsive again. Depending on the strength of the attack, the fighter, or just the complexity of the move itself, these phases can vary in the amount of time and therefore the amount of frames they last on screen. Generally, the strongest attacks take the longest to start up and recover from, but with the advantage that they deliver the most damage. Whereas the lightest attacks are the quickest to start up and have the shortest time to recover, but result in the least damage. Most expert Street Fighter players will have a good knowledge of when and how long these phases last, for each attack and probably for a number of fighters, which gives them advantage of knowing when to block and chain attacks, for example. Essentially, this boils down to frame counting. Let's bring up the original game again and use Ryu's light punch as a reference to show you what I mean. Looking at the animation array, the light punch only has 3 frames of animation in total, which probably makes it the easiest example. If we walk through the animation, frame by frame, the first is the startup phase, which lasts for 2 in-game frames. The next frame is the active phase, which lasts for 4 in-game frames. And finally, the last frame is the recovery stage, which also lasts for another 4 in-game frames. This equals a total of 10 in-game frames to complete the attack, at which point the fighter will revert back to the idle state. This method is generally applied to all the basic attacking moves, as you can see here with the medium and heavy attacks. Hopefully this gives you a little insight of how attacking moves work in Street Fighter. Going back to my original comment in regard to the light punch attack though, you should be able to rapidly press the control and perform the attack in quick succession. In terms of the attack phase that we've just described, it means this attack allows you to break the sequence and its animation prematurely, as seen here in the original game. Notice how the recovery phase is cut short when the button is pressed, and goes straight back to the startup phase. Okay, let's move on to adding this feature into our code too. So back in the fighter class in the handle light punch state function, we'll add a new check to see if the animation is less than the second frame, which we know is the recovery phase of the move. If it is, we'll just return from the function as there's nothing for us to do until that phase. However, if it is beyond that frame and therefore in the recovery phase, we'll check to see if the light punch control has been pressed, using the new isLightPunch function. If so, we'll simply reset the animation by setting the animation frame to 0. Okay, let's check what we have in the browser and compare it to the original game. Our version allows for the light punch to be performed just as rapidly as the original game. Great stuff. Let's now push forward and give the fighters some more attacking moves. We'll continue with the punches by adding both the medium and heavy basic attacks. We'll follow the exact same process for these moves as we did with the light punch. Starting with the control configuration, we'll add the medium punch and heavy punch properties to both the gamepad and keyboard objects. In regard to the gamepad button indexes, I'll now assign X for the light punches, Y for the medium punches, and RB for the heavy punches. I'll copy these values over to the second player's controls too, just like before. As for the keyboard, moving forward I'm going to be using my same key setup as I do for MAME. Player 1 will use the left alt for medium punches, and space for heavy punches. For player 2, I'll set up the W key for the medium punches, and the E key for the heavy punches. Next, in the input handler, as we've done all the heavy work when we set up the light punch attack, we just need to add 2 new functions to handle the 2 new attacks recovering. Simply copy the isLightPunch function twice, and we'll just amend the names to isMediumPunch and isHeavyPunch, and update and marry the controls constant for those two. Then, moving on to the Ryu and Ken classes, we'll again add the necessary frame data and animations for the medium and heavy punches. There's nothing unusual here, so if you need to pause the video for any of the details, please do so. Once they've been set up, we'll move on to the final part and glue up the state machine in our fighter class. Just like before, we'll create 2 new properties matching the remaining punch attacks, using the same naming convention for the init and update functions. Notice how we're using the same update function for both of these attacks. The valid from array will be exactly the same as the light punch, as these two attacks are again just standard punches. For both the init handler functions, we'll this time correctly call the reset velocities function, as just like before, we want the fighters to stop moving when initiating these attacks. We'll fix and update this within the handle standard light attack init function too, while we're here. You may be wondering why we have 3 separate functions for these, as they are all currently doing the same thing. Don't worry, this will come apparent in a future video. Moving on to the handle idle state function, yep, you guessed it. we'll add another 2 conditions using the isMediumPunch and isHeavyPunch control functions, and change the fighter's state to the corresponding attacks, if those controls are pressed down. Then, finally, we'll add one more function called handleMediumPunchState, which covers the update for both the medium punch and heavy punch states. In this function, we don't need to do anything special here other than to check if the animation has completed. If it has, we'll just revert back to the idle state. So with that in mind, let's move back up to the state machine and add both of these punch attacks to the idle state valid from property, so that we're able to do that transition. And that should be all that's required. With another check in the browser, you can see that all the standing punch attacks are now working as intended, both with the keyboard and the gamepad. So far so good. Okay, now that we have one set of attacks implemented, let's look to add the standing kick attacking moves next, as they work very much in the same way. We'll leave the crouching and jumping attacks for another video due to time, although again, they too also work in a similar fashion. So by now, we should all know how this works. We'll start back in the control configuration, and for the last time today, add the necessary properties to the gamepad and keyboard objects. For the gamepad, I'm using the A button for light kicks, the B button for medium kicks, and the RB button for heavy kicks. As per usual, we'll use these values for both gamepad objects, and therefore both players. As for the keyboard however, I'll again copy over the controls I use for main for both players. It should be noted that this is my personal setup that I use for dev purposes, but as I mentioned in previous videos, this controls object is completely configurable. So by all means go ahead and change these values to suit your own gamepad or keyboard setup as required. We'll next jump onto the input handler module, and again create 3 new functions that match the 3 different strands of kick attack. For ease, I'm just making a copy of the punch functions and amending the function names and control constants as necessary. In the right rank end classes, again we'll copy over the required frame data and animations for the 3 standard kick attacks. As per usual, I prepared this earlier, so I'll just copy it over. Please pause the video if you wish to copy this yourselves. Or if you wish, why not join my Patreon page and get access to the actual code? Okay, sorry, one plug per video I guess. Moving on to the fighter class, we'll now add the 3 new properties to the state machine to cover these new kick attacks. If you look closely, these attacks follow the exact same formula as the punch moves, even down to their init and valid from properties. The only difference is that they have their own update functions, which we'll create in a second. Scrolling down to the handle idle state function, we'll again add the 3 new kick attack control functions that we just created, and change the fighter's state to the corresponding kick attack state. Hopefully you're starting to see a trend now. And finally, we'll add the 3 update functions for the kick attacks too. Again, just for ease, I'm going to copy the punch functions and amend where necessary, as the code and states work in exactly the same way, with both the light and medium state function. Lastly, before we test what we've done in the browser, let's not forget to update the valid from property in the idle state in the state machine to include these 3 new kick states too. You'll have seen both Ryu and Ken now have all their standing punch and kick attack moves working as expected, which also include the necessary startup, active and recovery phases as previously described. Having some attacks to play with is a great step forward in applying the fighting mechanics, but what we really need now is those moves to actually cause damage to our opponent. For this to work, we'll need to know when and where the attack has collided. This leads us on to the next part of today's video, applying 2 more of the fighter's collision boxes, the hurt and active attack hitboxes. If you remember in part 7 of the series, we began to talk about these further collision boxes, where we actually implemented our first, the push boxes. This is currently being visualised by a green box, overlaid on the fighter's entity sprites, as seen here. Just like the push box, both the hurt and attack boxes are applied to the frame data. In regard to the hurt box, they are a set of 3 collision boxes, and are generally applied to every frame. I say generally, as some frames of animation don't have any boxes at all, but these are usually the exception, so are out of scope for this video. We may come back to this later, but for the frames we're covering today, they all have a set of 3 hurt boxes, and certain frames of an attack have hitboxes in their active phase. Let's delve into the hurt boxes first, and use one of the idle frames as an example. The 3 hurt boxes generally cover the head, body and feet of the frame, as shown by blue boxes from this point onwards. Notice in this instance, the hurt boxes are the same for all frames of the idle animation, although depending on the frame, these boxes will change position to ensure they cover the corresponding area of the frame it's attached to. For example, take this heavy kick animation. Notice how the boxes move around to cover the fighter as the animation plays out. Let's continue to have a look at the heavy kick animation, but this time with the hitboxes applied. Notice how there's a red box around the stretched out leg and foot on a number of frames. In fact, let's take a look at all the attack moves that we've added today and see how they compare. Just like the hurt boxes, these hitboxes are attached to the frame data, but unlike hurt boxes, the hitboxes only appear in the active phase of the attack. If these hitboxes come in contact with your opponent's hurt boxes, this is when an attack is connected and therefore causes damage. As we have 3 hurt boxes per frame, depending on which one has been collided with, it can be used to determine which part of the body has been hit. The advantage of this is that we can apply the correct corresponding hurt response. For example, if you were to hit the head versus the body, it will play a different hurt animation, or if you were to sweep the legs, the opponent will trip and fall. Let's now go ahead and look to apply these new collision boxes to our code and frame data. Starting in the Ken class, let's go back to the frame data and add the necessary hurt boxes to the idle frames as the first example. We're going to add another array to the end of the frame, and inside that create a further 3 arrays which represent the head, the body and feet box dimensions. As these are dimensions, they'll each contain 4 values. The first 2 values are the X and Y positions of where the box starts, based on the frame's origin point as an offset, and the next 2 values are the width and height of the box. As we know that each of the idle frames have the same hurt box dimensions, we'll copy these arrays and values to all the idle frames. Good thing for us is that both the Ken and Ryu classes have the same hurt boxes, so we can copy these values over to the idle frames in his class too. Then, in the Fighter class, as we now have more than one collision box, we're going to make our first refactor today. We'll rename the current pushbox local property to boxes and contain the current pushbox object inside it. We'll next rename that property to just push and add a new property called hurt. This new property will be used to house the current frame's hurt box dimensions. For this reason, we'll copy the array structure we used for the frame data, giving each a default value of 0. We'll then move down to the getPushBox function and update it to cater for the refactoring we've just done. We'll first rename it to a more clearer name of getBoxes, before moving on to the destructive values from the frame's getObject function. Let's amend this now to deconstruct the new hurt boxes we've added. We're assigning these to a new head, body and feet variables here, and giving them a default value of 0s just like before. We give them this default value to ensure that we don't deal with any undefined values. We'll also deconstruct the pushbox the same way, using temporary x, y, width and height variables, just for the time being. Then, for the function's return, we'll update this so that it matches the class's local box's property object structure, having both push and hurt properties. We'll then move down to the update animation function and refactor that next. We'll start by making the code a little simpler, by returning early rather than using nested if statements. First on the animation time condition, and then on the frame delay condition. And while we're here, we'll also shorten the animation frame condition too. Although the main change we want to perform is to amend the pushboxes assignment, changing it to use the new local property boxes, and for it to use the new getBoxes function instead. As we've moved this line to the bottom to ensure we get the correct box data for the frame, we now can't use the frame key either, as it'll be out of sync. So we'll remove that and use the direct reference to the animation index instead, based on the animation frame. For the next refactor, we'll go about renaming all the pushbox references to use the new boxes object instead. For this, I'm simply going to use the find and replace functionality from VS Code, changing this.pushbox to this.boxes.push instead. The last refactor will be the drawDebug function. So let's move down to that and amend the line where we call the getPushbox function, which we know will be renamed to getBoxes. When doing large refactors like this, it's always wise to check you haven't broken anything, so let's quickly do that. And it looks like everything is fine. Okay, let's continue then. With those refactors now in place, we just need to visualize the hurt boxes in game to ensure they work as intended, just like the push boxes. Luckily, we're already in the place where this magic happens, the drawDebug function. As we're drawing more than one box to the screen now, it's best to move this logic to its own function. Let's do that above the current function, and call it drawDebugBox. This function will take both the context and camera as per normal, but also a dimensions array and a base colour for the box we're going to draw. Inside, we'll do a quick check to ensure the dimensions parameter is an array, and return out early if it's not. This is to ensure that we don't pass on any incorrect formatted objects instead. We'll then deconstruct the x, y, width and height values from it, as we definitely know it's an array at this point. We'll then copy the current box drawing code from the current drawDebug function and move it here instead. We'll then update both the stroke and fill style context properties to use the base colour parameter we passed into the function instead of barcoding it. Notice how we're appending an AA to the stroke colour and a 44 to the fill colour. These are the alpha values, meaning the fill colour is more transparent than the stroke colour. The last thing we'll do here then is correct the rect context function calls to use the dimension variables we've created. And we now should be able to call this new function within the drawDebug function to draw the collision boxes. For the push box, we'll replace the current code and pass on the box.push property for the dimensions, and use 55FF55 as the colour, which is the hex value for light green. Then onto the hurt boxes. As we have 3 of them, we'll iterate over the boxes.hurt property using a for loop. This time when calling the drawDebug function, we'll pass on the temporary hurt box variable as the dimensions, and 7777FF as the base colour. This should draw all the hurt boxes using the light blue colour. We'll prove that point in a second, but before we do, we'll have to wrap the box.push variable in an object.value function, as it's actually an object due to how we use it in the code, but for our function we only need the values from it. Honestly, if this was game code too, I'd probably look to cater for this a little differently, but as this is just a debugging code, and therefore something we would normally turn off, it's not overly important. Okay, opening up the browser, we can see that we now have both the hurt and push boxes drawn around the fighters, while they're in their idle state. As we move out of that state, you'll notice the hurt boxes disappear, as we yet don't have those hurt boxes defined. Although, as we did supply some default values for them, the game doesn't just fail. Good stuff. Looking at one of the fighter classes, you'll notice that we have some repetition now for the hurt boxes across the idle frame data. And to be fair, this same hurt box data needs to be applied to a number of the standing frames also, causing more repetition. To make this easier on ourselves, I'm going to follow the pattern we applied to the push box argument and extract this data into its own lookup object. So in the fighter constant module, we're going to create a new object called hurtbox, just like the pushbox object above. We'll define the most common values used for most frames. We can then reference these instead of repeatedly typing them out. In fact, instead of typing them out again myself, I'll copy over a number of properties I prepared earlier. As you can see, these cover most of the fighter states. Let's move on to the fighter classes now and implement these new properties along with any outstanding hurt boxes to the rest of their frame data. We'll do this in both the Ryu and Ken classes, but as per usual I prepared this data before, so I'll be copying the details over to make this easier for everyone. Again, please pause the video if you wish to copy any of these values. Notice that most of these frames use the predefined hurt box values we just created, including the idle frames from earlier. Although there are a few frames that have bespoke values here, so these have been handled and entered separately. If you feel like it, all these values could be placed inside the hurtbox object, but I prefer to keep them separate so I know which ones are bespoke boxes versus ones that I've used multiple times. And just before we leave these classes, let's remember to add the hurtbox reference to their input lists. Checking the results in the browser now, and you can see that both Ryu and Ken have their necessary hurtbox data applied to their animation frames. This includes all their current states, including the idle state from earlier. Let's continue this process and now apply the necessary hitbox data to the required frame data. If you remember, these only appear on certain frames, but still work very much in the same way as the hurtboxes. So back in the Ken class, we'll start by applying the hitbox data to the light punch attack first. This again is another array that we'll add to the end of the frame data, and again will be another set of dimensions that has the same structure as the hurtboxes, meaning the values are based on the frame's origin point. For the light punch attack, we only have a hitbox on the light punch 2 frame, so we'll only need to add the required data there for now. We'll apply the same hitbox for the Ryu class too, as again this has the same hitbox data. With the first hitbox in place, we'll move on to the fighter class and add the necessary property to the boxes object. This will follow the same structure as the push box, so we'll copy that as the default value. The reasoning for this will become apparent later in the video. Moving down to the getBoxes function, we'll apply the same changes here too, deconstructing the hitbox array from the frame data. We'll copy the push box to start with and amend the variable names to use hit as the prefix. And to finish off, we'll add the new hit property to the returned object. Again copy the pushbox structure as the base, and then amend the property names to use the deconstructed hitbox values. Finally, we'll move down to the drawDebug function and add a call to the drawDebug box function using the new hit property. Just as before, we'll copy the pushbox call and amend as necessary. We're using a hex value of FF0000 for the colour, which is a bright red, so this should make it fairly visible. With another check in the browser, if we press the light punch attack now for either Ken or Ryu, you can clearly see a red box around the attacking arm. This means we can confirm that the hitbox is now attached to the active phase of the move. Although, if we were to perform any of the other attacking moves, you can see we're currently missing the hitboxes for those, so let's look to quickly fix that next. Starting in the Ken class, I'm going to add the remaining hitboxes to all the attacking moves. As per usual, I'll be pasting this in from my predefined code. We'll do exactly the same for the Ryu class too, highlighting the attacks and pasting in the missing hitboxes. Again, please go ahead and pause the video if necessary. Checking the results in the browser again, we can see that both Ryu and Ken now successfully have their hitboxes applied to their punch and attack moves where necessary in the active phase. So for the last thing in today's video, let's look how we can add some temporary logic to check for the collisions between the hitboxes and the opponent's hurtboxes. Back at the fighter class, we'll add a new update function called updateAttackBoxCollided above the main update function, which will add a call reference to the bottom of that function. We'll pass on the time value too, which to be fair we probably won't use just yet. In this function we'll be checking to see if the current fighter is in an attacking state, and if so, check to see if the current frame's hitbox is overlapping the opponent's hurtboxes. So first things first, we're going to need to check if the fighter is in an attacking state, because if they're not, we can simply return out of this function as there's no reason to continue. As we're talking about states, let's move back to the state machine and specifically to the new attack moves we've added today. If we were to look at the states themselves, you currently don't have anything distinct to determine which are attacking state versus which is a non-attacking state. So we'll fix this by adding a new property to each of the attacking states, called attack type. This new property will serve two purposes moving forward. The first, which we'll be using today, as mentioned, will allow us to decide if a state is an attacking one, but secondly, which of the attacking states are punches and which are kicks. This will come in handy in part 11, but more on that then. Before we can do this however, let's jump back to the fighter constant module and add another enum object called fighter attack type at the top of the file. This will have two properties for now, called punch and kick, to allow us to group together the different attacking types. Okay, back in the fighter class then, we'll import this new object into the import block, although it seems to be getting a little crowded at the moment, so we'll clean it up a little first before moving on. Then back in the state machine, we'll go ahead and add the new attack type property to each of the attacking states, and set it with the correct fighter attack type constant value. Okay, let's now go back to the new update attack box collided function we created. As mentioned, we'll add a quick check to see if we're currently in an attacking state, by checking to see if the current state has a defined attack type, because as we know, this property is only applied to the attacking states. The next challenge is to convert both the hurt and hitbox's dimensions into actual screen dimensions, so that we can check to see if they overlap. Unfortunately, they are both currently defined in relation to the fighter's origin point, which isn't too helpful at the moment. So in the collisions module, let's create a new helper function that will do this for us. We'll call this function getActualBoxDimensions, and it will take a position parameter, which will be the fighter's origin point, the fighter's direction, which we know can either be 1 or -1, and finally the box dimensions itself. Inside this function, let's first set up the returning object with the actual dimension properties. Using Ken's heavy punch hitbox frame as an example, let's start with the easy values first, which will be the width and height properties. For these values, we'll simply pass on the hitbox width and height values. For the Y dimension, this will be a combination of the Y origin point plus the hitbox's Y position. Then finally for the X dimension, we need to discover where the leftmost X value is of the actual box based on the fighter's direction. In the first pass, we'll take his X position and then add the hitbox's X position to it, which in turn is multiplied by Ken's direction value. By default this will be a positive number, although if he's facing left, the direction value will be -1, which will result in a sign value, meaning it will be negative. For the second pass, using the first value, we can do a similar calculation again, but this time with the hitbox's width value. Having both of these values, we can now use the mathmin function to determine which of these X values is the smallest, which results in the leftmost value. And there we have it. Any box value we pass in now will get the actual screen dimensions it possesses. Back to the update attack box collided function. Let's now call this new helper function and pass on the local position, direction and hitbox properties. We'll then iterate over the opponent's hurt boxes using a for loop. Inside this, we'll first deconstruct the dimension values from the current hurt box in preparation for the next step. Next we'll use the helper function again to get the actual screen dimensions of the opponent's hurt box, passing on the opponent's position and direction, along with the deconstructed dimension values as a box object. Now that we have the actual hitbox and the actual opponent's hurt box dimensions, we need to check that they overlap. Luckily for us, we already have a Rex overlap helper function defined, but unfortunately it requires the arguments to be spread out over the function call. Okay, let's create another helper function that simply spreads out our dimension boxes for us. Back inside the collision module file again, we'll create a new function called boxOverlap, which will take two dimension objects as parameters. Inside we'll simply return the Rex overlap function result from above, but we'll spread the box's dimension values individually. Simples. Reverting back to the fighter class, we'll now call this helper function and pass on the actual boxes we just obtained, meaning this will return true or false if these overlap. We're actually checking to see if they don't overlap, because if they don't, we can again simply return out of the function. It's at this point we know that we have an attack collision, so we can respond as necessary. We'll develop this further in the next part of the series, where we dive into the global state. But for now, we'll just print out a message to the console to prove that it's working as intended. Let's first get the index of the hurt box, so we know which part of the body the attack is overlapping with. We'll do this by using the index of function, and passing on the hurt variable. This will return an index number between 0 and 2. We'll then log a message with the collision details to the console, so we know which collision has happened. I'm using an interpolated string here, using the fighter's names and the hurtbox index that was triggered. The hurtbox index isn't much to go on, so let's create another small array with a set of named strings. so that we can translate the index into a readable string for the console message. Let's add this new array name to the end of the message, and now use the hert_index variable as the index to the string value. Returning back to the browser, we'll quickly open up the DevTools window and see the results that this produces. Everything seems to be working as intended. As the fighters attack their opponent, we're correctly logging a message to the console with the details that inform us who attacked who and where. Good stuff. So, in between the code and the progression we've made today, we seem to have only added the attacking moves to the idle state, but in fact, these can be added to both the movement states too. Let's quickly remedy that. Back in the fighter class, we'll copy all the attack controls from the handle idle state function, and simply paste those lines into the walk forward and walk backward state functions, and that's basically it. Just jumping back to the browser again, we should now be able to perform an attack while moving back and forth, just as you did in the original game. And as per usual, before we close today's video, let's look at making some small refactors so that we can clean up the code a little. The first one today will focus on the frame delay value within the animations of the Ryu and Ken classes. As we know, this value is based on the time we'd like the frame to last for before advancing to the next frame. Although as we've learned today, Street Fighter is pretty much tied to the game frames, which we know has 16.6 milliseconds per frame. To make this easier on ourselves, I'm going to change this frame delay value from milliseconds to actual frame counts instead. We can then use the new frame time constant we created in the last video to work out the actual milliseconds value automatically for us. Let's look at the idle animation. You can see all these frames use a value of 66, which if we divide this by the frame time value of 16.6, this gives us 4 frames. So this is the value we'll change it to. Although again, instead of typing these out, I'm going to copy over what I prepared earlier. First in the Ken class, and then the same in the Ryu class. As we know, both fighters have the same animations. To make the animations work using frames, we'll need to amend the update animation function within the fighter class. On the line where we're checking if the frame delay has exceeded, we'll simply multiply this value with the frame delay constant value, and that should do the trick. Although I've had to import the constant value manually here, because for some reason, VS Code didn't want to do it automatically for some reason. For the next refactor, we'll look to split the control module file, as currently it has 2 responsibilities, one to hold the constant values, and secondly, one to hold the configuration object. Let's add a new folder called config within the source folder, and then add a new module file called controls.js. As you can probably tell, this new file will hold the configuration side of the controls. So we'll cut that object from the control module file, and simply move it to this new file, not forgetting to update the input reference within the input handler module file. And for the last refactor for today, we'll hop over to the fighter class again, and make a couple of final changes there too. The first within the reset velocities function, where we'll take the current code and merge it into one line, so that it's more precise. And then within the change state function, we're going to add a small console debugging message in the initial return condition. This message will inform us whenever we try to make an invalid transition, detailing the initial state and the state we're trying to move to. This will become very handy when we're trying to add new code and ensuring we're populating the valid from properties within our state machine. Okay, I think that'll do us for this video. So for the last time today, let's check the results in the browser. And it seems everything is still working as it should, including the animation timings we've amended. Opening up the DevTools, we can see that the collisions are still being reported correctly, along with some transition errors, which on one hand is good, as we're guarding against them, but on the other hand, we should probably look into why these are happening too, in a future refactor session. So let's quickly recap on what we've accomplished in today's video. And to be fair, it's quite a lot. Firstly, we've added 6 new attacking moves to the state machine. These were the 3 standard punches and kicks in their varying strengths. We've updated the control schemes to accommodate these new moves, while also allowing for key presses to ensure we got the correct response from the attacks. We then learnt about the different phases of an attack, which allowed us to implement the new collision boxes to the necessary animation frames. Finally, these certain hitboxes were then used to detect if we hit an opponent from an attack, where we added a temporary message to the console. We'll look to expand on this in the next video, where we'll discuss the global, or battle state, applying the hit animations and reflecting the attack's damage and score in the status HUD. We may even look to add the missing crouch and jumping attacks too, if we get time. So yeah, as per usual, there's still plenty to get on with. But first things first, let's sign off. Again, we've had some delays between videos, mostly with illness this time around, where it affected my voice and I couldn't record any vocals for over 2 weeks. I even had to go back to the track on this video to re-record some of the vocals, so apologies all round on that one. Please let me know if you notice any issues. Unfortunately, I have to mention again that I'm finding these are taking longer to complete at the moment due to exploring the game's more complex topics now. As you can see, the videos are steadily increasing in length too. We're nearly at the 40-minute mark. So with that in mind, I'll be moving to only posting these once a month moving forward. Especially with Christmas and the New Year coming up in the coming weeks, where my normal life will get in the way. As mentioned previously, I regularly drop update messages on my Patreon page if you'd like to keep up with the latest news, but I have recently got access to YouTube's community posts, so I'll be making use of that too. I do plan to work on the main codebase again in the coming weeks, where I'll be tackling special moves, so any top tier patrons can expect that to drop soon. Once that's done, a vlog will no doubt drop soon after too, as I've not produced one of those for a while now. And finally, thanks again for everyone's support so far. I'm extremely appreciative of all the likes, comments and subscriptions, both on this channel and my Patreon page. A big shout out to all my Patreon supporters here too. You're the guys who spur me onwards. And with that, I'll say my goodbyes, and hopefully I'll see you in the next one. And out.